Air cargo remains a key element of global trade, carrying 35% of total trade measured by dollar value. The value of air cargo to world trade has been further highlighted during the COVID-19 pandemic, as the need to ship critical medical supplies and equipment quickly, securely, and over long distances has been underscored throughout 2020. According to the Boeing 2020 Commercial Market Outlook, it is predicted nearly 2,400 freighter aircraft must be delivered within the next 20 years to account for market growth. In this expansion, one potentially underserved area is easily moving freight to and from the more outlying areas to the larger cargo hub airports. These outlying regions are currently served by small cargo aircraft or by road trucks, where cargo needs to be unpacked and repacked for the smaller transport, greatly slowing distribution of critical supplies. The utility freighter with standard ULD capacity and minimal loading and unloading labor is the solution. Design began with concept sketches identifying key features such as initial loading ideas, cargo door placements, and wing configurations. The first CAD model developed included fully completed design details, a product of calculations obtained from Raymer's aircraft design textbook, which was extensively used in the design approach. Some key features established in this first iteration are the proposed fuselage cargo deck layout and the first wing and tail design. The high wing configuration and T-tail design were decided on for their advantageous loading clearance and high stall angles. As the aircraft model was developed, each stage of design and integration was highly focused on the aircraft's flexibility of operations. Adjustments to wing incidence, aspect ratio, and airfoil selection were picked to achieve a range of at least 1,000 nautical miles at a cruising Mach of 0.7. The landing gear configuration and fuselage dimensioning directly yield the aircraft's capability to load and unload with minimal ground handling equipment, as well as the inclusion of a main deck cargo inspection aisle and lower hold bulk cargo compartment. Much of the propulsion development was directly focused on fuel efficiency, climb gradient requirements, and runway distance specifics, as well as the weight considerations that in turn affect every piece of the aircraft design. The Boeing Husky utility freighter with a 15-ton capacity is mainly identifiable by its high wing configuration and two main cargo doors. The aircraft flight deck can sit 2 pilots, along with 3 additional crew members. The fuselage is designed to carry 5 AMA M1 cargo units. Its doors placed on either side of the wing root to allow for ease of access and for more efficient loading. To begin data comparison, OpenVSP was used to yield lift, drag, and the desirable aerodynamic coefficients that could be compared to data collected from wind tunnel testing. Each model was developed and tested in the 3x3 wind tunnel. Analysis alongside the OpenVSP results provided the validation of our conceptual design. Approximate block fuel numbers can be identified from our target range, engine capabilities, and fuel capacity. The Balto sits at 840 pounds of fuel per ton cargo, considering a 1,000 nautical mile range, while other similar aircraft such as the Boeing 737-800 and the Airbus A321 have significantly lower fuel efficiency for their cargo capability, with 1,040 pounds of fuel and 1,090 pounds of fuel per ton cargo respectively. Other than the ease of cargo loading and unloading and its flexibility of airport service, the Balto clearly outperforms its competition in fuel efficiency and cargo capability. This utility freighter can successfully mitigate small-scale air cargo distribution issues and provide a new solution to critical supplies reaching outlying regions.